this lecture, we will look at certain special counting techniques, including the addition and multiplication laws, the concept of factorials, and enumerating permutations and combinations. We say that two events are independent if their outcomes are not affected by each other. Often in some branches of mathematics, we will want to find the total number of possible outcomes when multiple events occur together. The addition law states that given two independent events E1 and E2, the number of ways either E1 or E2 can occur is the sum of their individual numbers of outcomes. For example, if a menu contains 5 main dishes and 4 desserts, the number of possible one-course meals is given by the sum 5 plus 4, or 9. The multiplication law states that given two independent events E1 and E2, the number of ways that E1 followed by E2 can occur is the product of their individual numbers of outcomes. For example, if a menu contains 5 main dishes and 4 desserts, the number of possible two-course meals is given by the product 5 times 4, or 20. For example, consider a system where 3 towns A, B, and C are separated by one-way streets. Suppose there are 4 one-way roads from A to B and 3 one-way roads from B to C. We could represent this with a labeled diagram like so. We could then ask, how many different ways are there to get from one town to an adjacent town? We could also ask, how many different ways are there to get from town A to town C? For the first problem, note we are asking how many ways there are to get from town A to town B, or from town B to town C. We can list them in sequence to see that there are 4 plus 3 equals 7 total ways. Notice, since this question asked for the outcomes of one event or another independent event, the addition law applied. For the second problem, note we are asking how many ways there are to get from A to B, and then from B to C. We can list all possible routes in a table to see that there are 4 times 3 equals 12 total ways. Notice, since this question asked for the outcomes of one event and then another independent event, the multiplication law applied. A permutation of a set of objects is an arrangement of objects in which their order is important. For example, how many ways can 5 people stand in a queue? This is the same as asking how many permutations are there of 5 different objects. Filling out the queue per position, we first have a choice of 5 people to stand in the first position. Next, we have 4 people remaining who can fill the second position in the queue. Then there are 3 people to choose from for the third position, 2 people for the fourth position, and the final remaining person can take the final position in the queue. Because each of these events occurred together, the multiplication law applies, and so the total number of outcomes is 5 times 4 times 3 times 2 times 1, or 120. In general, the product of all the positive integers less than or equal to a number is known as the factorial of that number. The factorial of a number n is denoted by n followed by an exclamation mark. For example, 5 factorial is 5 times 4 times 3 times 2 times 1, which we just saw to be 120. Similarly, 6 factorial is 6 times 5 times 4 times 3 times 2 times 1, or 6 times 5 factorial, which is 720. In general, we have that the number of permutations of n different objects is exactly n factorial. Also, note that an unusual special case of the factorial function is that we take 0 factorial to be 1. Let's look at some counting examples that utilize the factorial function when enumerating permutations. For example, in how many ways can 5 boys and 4 girls be arranged in a line? Since the people have been arranged in a line, we can assume that the order they are arranged in matters. Because there are 5 boys and 4 girls, there are a total of 9 people to be ordered. So the total number of arrangements is given by 9 factorial, which turns out to be 362,880. Now consider finding how many ways to arrange the 5 boys and 4 girls if boys and girls must alternate. This means the pattern they must stand in is given by boy, girl, etc. So we can first arrange the 5 boys in any order and place them in the odd-numbered positions, and then arrange the 4 girls in any order and place them in the remaining positions. Since these events occur together, we must multiply their outcomes, so the final result is 5 factorial times 4 factorial, or 2,880. Next, in how many ways can 5 boys and 4 girls be arranged in a line so that the boys and girls are in separate groups? The group of boys and the group of girls can be positioned in either order. Since these two groups need to be arranged, there are 2 factorial ways to do this. Then, within the group of boys, we can arrange all 5 in any order, and within the group of girls, we can arrange all 4 in any order. So the total number of arrangements is given by 2 factorial times 4 factorial times 5 factorial, or 5,760. Finally, in how many ways can 5 boys and 4 girls be arranged in a line so that 2 particular girls are next to each other? In this case, it is useful to think of the 2 girls who wish to be neighbors as a single unit. Within this particular unit, the girls can be arranged in 2 factorial ways. To form the line, we then want to order the other 7 people along with this combined pair of people. Considering the 7 individuals plus the 1 pair as 8 different units to be arranged, we can do so in 8 factorial ways. So altogether, there are a total of 2 factorial times 8 factorial, or 80,640 ways. We can also think of permutations of a subset of a group of objects. The number of permutations of R objects chosen from N objects is denoted by a superscript N followed by a capital P followed by a subscript R. For example, how many ways can 3 people chosen from 5 people stand in a queue? This is the same as asking for the value 5p3. Filling out the queue per position as before, we first have a choice of 5 people to stand in the first position. Next, we have 4 people remaining who can fill the second position in the queue. Finally, there are 3 people to choose from for the third position. So the total number of outcomes is 5 times 4 times 3, or 60. Expanding this product out so that it resembles a factorial, we can multiply it further by 2 and by 1 before dividing out again by 2 times 1. So in terms of factorials, this value is 5 factorial divided by 2 factorial. We can see now that in general, the number of permutations of R objects chosen from N objects is given by the product of N, N-1, N-2, and so on, until R terms have been multiplied together. In terms of factorials, this is given by N factorial divided by N-R factorial. So for any R between 0 and N, we have a general formula for NPR in terms of factorials. Another concept similar to a permutation is known as a combination. A combination of R objects chosen from N objects is simply a group of R objects in which order does not matter. The number of combinations of R objects chosen from N objects is denoted by a superscript N followed by a capital C followed by a subscript R. For example, how many ways can 3 people be chosen from 5 people? Since we no longer care about the order the people are chosen in, this is the same as asking for the value of 5c3. In the case where the order of selection does matter, we know that there are 5p3 total arrangements. However, counting groups in this manner would, for example, consider the group formed by selecting the people A, then B, and then C, different to the group formed by selecting B, then C, then A, despite these ultimately forming the same group. In fact, the group of people A, B, and C would be counted 6 different times in this case, since there are 3 factorial, or 6, different ways to arrange the people A, B, and C. This means that in general, each group has been counted 3 factorial times instead of once. So dividing through by this overcounting factor, the total number of groups formed is given by 5p3 divided by 3 factorial, or in terms of factorials only, 5 factorial divided by 2 factorial, 3 factorial. We can see now that in general, the number of combinations of R objects chosen from N objects is given by the number of permutations of R objects chosen from N objects divided by a factor of R factorial. In terms of factorials, this is given by N factorial divided by R factorial times N-R factorial. So for any R between 0 and N, we also have a general formula for NCR in terms of factorials. Let's now look at some counting examples that incorporate enumerating combinations and permutations. For example, in how many ways can 7 women and 4 men form a committee of 5 people? Since a committee of people is an unordered group, We are counting combinations as opposed to permutations here. Since there are 7 women and 4 men, there are 11 people total to choose from. So the answer is 11C5, or 462. Now, suppose we wish to form a committee under the same circumstances, but this time each position in the committee has a different named role. Then in this case, the order the members are selected does matter, so we are counting permutations as opposed to combinations here. Therefore the answer is 11P5, or 55,440. Next, what if we wish to form a committee of 5 from 7 women and 4 men, where within the committee there is a president, a vice president, and a secretary? This time, the order of selection partially matters and partially does not, so we expect to use both the permutation and combination formulae. For example, we could first choose an unordered group of 5 people from the original 11 for the committee, and then choose 3 people from amongst these 5 in order to take the 3 named roles. This means the total number of arrangements is given by 11C5 times 5P3, or 27,720. Alternatively, we could first fill the named positions by selecting an ordered group of 3 people from the original 11, and then choose an unordered group of 2 extra people from the remaining 8 to take the 2 unnamed positions. This means the total number of arrangements is also given by 11P3 times 8C2, which again resolves to 27,720. Now suppose 2 particular people amongst the 11 do not wish to join the committee. We can deal with this problem by removing them from the original pool of people before selection. This means we are now choosing a group of 5 people from just 9 people. So there are 9C5, or 126 total ways. Suppose instead that out of the 7 women and 4 men, the committee must comprise of 3 women and 2 men. Then we can first choose 3 people from the group of 7 women, and then choose 2 people from the group of 4 men. Then the total number of arrangements will be 7C3 times 4C2, or 210. Sometimes it is easier to count a set of arrangements by instead finding the size of the complement, or opposite, of the set, and subtracting this from the total number of arrangements in general. For example, in how many ways can 7 women and 4 men form a committee of 5 people in which there is at least 1 man? The complement of those committees with at least 1 man is the set of committees with no men. Since this is easier to calculate, let's find the size of the complement set and subtract it from the total number of possible committees in general. Here, the number of committees with no men is the number of committees with only women, found by selecting 5 people from the group of 7 women, or 7C5. The total number of all possible committees is just 11C5, so our answer to the total number of committees with at least 1 man is found by subtracting 7C5 from 11C5, which gives 441. Similarly, let's try to find in how many ways 7 women and 4 men can form a committee of 5 people if 2 particular people cannot be in the committee at the same time. In this case, the complement of those committees which don't contain 2 particular people at the same time is exactly those committees which do contain those 2 particular people at the same time. To find the number of committees containing both these people, simply select these 2 first, and then fill the remaining 3 places on the committee by choosing 3 people from the remaining 9. This means that the total number of committees that don't contain both these particular people is given by 11C5 minus 9C3, or 378. In summary, we have seen that the outcomes of independent events can be combined using the addition and multiplication counting laws. We have also defined the factorial function and seen how to calculate permutations and combinations combinatorically as well as algebraically in terms of factorials. These laws and formulae can be incorporated together in different ways depending on the design of a counting problem, as we have seen by considering several examples.